Hi everyone! Salamat sa inyong patuloy na ginagawang pagsubaybay dito sa ating discussions about mechanics of deformable bodies. In today's discussion, we shall have thin-walled pressure vessel. And in particular, we shall have some derivation of the formula on how do we compute the magnitude of a thin-walled pressure vessel. On the later part of this discussion, I have prepared for you sample problem which will show you and guide you how to compute a problem that deals with thin-walled pressure vessel. Let's start with our discussion what a thin-walled pressure vessel is. When we say a thin-walled pressure vessel, it is actually referring to a vessel that contains a pressure inside and whose thickness of the wall is very, very thin. And because of the thickness of the wall is subjected to stresses due to the bursting effect of the pressure inside the vessel. As we have here, we say that a tank or pipe that is carrying a fluid or gas under pressure is subjected to tensile stress which resists the bursting effect of the pressure. And so if you have a cylindrical tank, stresses are developed across longitudinal and transverse section. I have here a sample of a cylindrical tank which may probably contain pressure inside. If this tank will contain pressure inside, then this tank will be subjected to the bursting effect along the longitudinal direction and along the transversal direction. And to show how this could be computed, let us imagine that we have here our vessel, and let this vessel be cut into two by a cutting plane, so that the vessel will be subdivided into the left and the right component of the vessel. And I will show you here what will happen. Suppose that we try to isolate the two parts of the vessel. In particular, I would like to consider the left part. And here is what will happen. Due to the pressure inside, then this vessel will be subjected to a bursting effect F. That bursting effect shall be equal to the product of the internal pressure multiplied by the projected area upon a plane perpendicular to the longitudinal axis. If we are to show the projected area upon a plane that is perpendicular to the direction of the longitudinal axis, then it will be a circle. And therefore, the bursting effect shall be equal to the product of the internal pressure multiplied by that area, which is in the form of a circle, whose formula is equal to pi d squared over 4. Due to this bursting effect, the wall of the cylinder will be subjected to a tensile load that will resist the bursting effect of the pressure. And if you are going to apply the condition of equilibrium, it will lead that the magnitude of this tensile load shall be equal to the magnitude of the bursting effect. And this will also be equal to the product of the pressure inside multiplied by the area projected upon the plane perpendicular to the direction of the longitudinal axis, which is in the form of a circle. And that is also equal to pi times pi d squared over 4. And then if we were to compute the stress on the wall, this can be computed as the ratio of the tensile load over that of the resisting area, where the tensile load is equal to the pressure inside multiplied by the area of the circle, and the resisting area shall be equal to the circumference of this circle multiplied by the thickness of the wall, and that is equal to pi dt. And so if d will cancel, pi will cancel, as well as d will cancel, therefore the resulting stress will be equal to the pressure inside multiplied by d divided by 4t. And if we were to ask what type of stress is this stress is called the longitudinal stress because the stress is directed along the longitudinal axis of the vessel. Kaya siya tinawag na longitudinal stress because the direction of this T that causes stress on the wall of the vessel is directed in the same direction as the longitudinal axis. Kaya ang tawag sa kanya is longitudinal stress. Now suppose that the vessel is cut on the other direction. Suppose that the cutting plane now is to cut the transverse section of the vessel such that we will have this cutting plane. If this cutting plane is to cut the vessel in this form, then we have cut the vessel along this transverse section. And if you are to isolate the lower part of this exploratory section, then this is what we shall have. We shall expect that the lower part, due to the pressure inside, will be subjected also to the bursting effect F. And the bursting effect F is equal to the product of this pressure inside multiplied by the area of the cut section projected perpendicular to the direction of the bursting effect. And if you are going to look from the top, then we will be looking at the section in the form of a rectangle having the dimension equal to the length of the vessel and the diameter of the vessel. Hence, the magnitude of the bursting force is equal to the product of the internal pressure multiplied by the area of the section cut by the cutting plane projected perpendicular to the direction of the bursting force. And so, if this will be substituted with the value, therefore, the bursting force F shall be equal to the internal pressure multiplied by the diameter multiplied by the length of the vessel. And this vessel will be subjected to a tensile load acting on the wall of the cylinder to resist the bursting effect of the pressure. And this will be seen as all those forces acting on the wall, as you would see in the illustration. So these forces may be summed up as T. And if we're going to apply the condition of equilibrium, we would expect that this T will be equal to the magnitude of that bursting effect. And so we have T equal to the bursting force, and that bursting force is equal to the pressure inside multiplied by the diameter and the length of the vessel. Therefore, T will be equal to P times D times L. And if we are to compute the stress that this T is causing upon the wall, then it will be computed as the ratio of the tensile load to the resisting area. Thus, the stress will be equal to the ratio of the tensile load over the resisting area. And what is this tensile load equal to? The tensile load is equal to the pressure inside multiplied by the diameter multiplied by the L, while the resisting area is equal to twice the length of the vessel multiplied by the thickness. Because you have here the length of the vessel on the one side and the other length of the vessel on the other side. And you might be asking, why we don't consider the thickness of the wall on the cover. The answer is this: if the vessel is very, very long, then this wall, this thickness of the cover is ineffective in helping the wall to resist the tensile stress or the tensile load, particularly if this wall is somewhere at the middle. And because this is ineffective in helping the stress, particularly if the member is somewhere at the middle, therefore they are neglected in the computation for the stress, and it is assumed that only the wall of the vessel is carrying the tensile load that resists the bursting effect. And therefore, the total resisting area is just equal to twice of the length of the vessel multiplied by the thickness. And therefore, if this will be simplified, L will cancel, therefore stress will become equal to P times D over 2T. And how do we call this stress? This stress is called a tangential stress because the stress is directed tangent to the surface of the cylinder. Sometimes they are also called circumferential because it is acting along the circumference of the cylinder. And it is also called sometimes as the hook or geared stress. Now, I have here some very important thing to let you know that the stress formula that I have just presented are only applicable for cylindrical or long pipes. Take note that we have derived two formula. One formula is the stress developed along the longitudinal axis, which is also called as the longitudinal stress, and is defined as the stress equal to P times D over 40. And the other one is the stress caused along the circumference, and it is equal to P times D over 2T. And you will notice that tangential stress is as much as the stress developed along the longitudinal stress. But again, those formula that we have just seen are only applicable for vessels that are in the form of a cylinder or in the form of a long pipe. Now, for vessels having different sections or shapes other than that of a cylinder, then the vessel is subjected according to the following. Letter A. If the vessel have the same dimension in the three directions. Ibig sabihin nun, ang vessel daw, ang dimension ng vessel ay pare-pareho in the three directions. Ano? Okay, then, the magnitude of the stress is the same in all directions. Ano? Is the same in all directions. And the magnitude is equal to the ratio of the bursting effect due to the internal pressure and the resisting area, which is equal to the circumference of the area of the cut section multiplied by the thickness of the wall. So I will show you an example. Ano bang halimbawa ng tinatawag nating vessel that have the same dimensions in three directions? Isang halimbawa, spherical tank. Diba? Spherical tank kasi ang dimension niya in the X, in the Y, in the Z directions are the same. Ano pa? Halimbawa, meron tayong cubical tank where the dimensions of the sides are the same in the X, in the Y, and in the Z. So if we have those kind of vessel where the dimensions are the same, then we shall be getting only one magnitude of the vessel in the three directions. And the magnitude is equal to the ratio of the resisting force, the bursting force divided by the resisting area. Now, to show you an example, let us have here a spherical tank where here is shown the three mutually perpendicular axes, the X, the Y, and the Z direction. And as we observe, the dimension of this vessel in the X, in the Y, and in the Z directions are the same. Ngayon, sabihin natin that we have here a cutting plane that is parallel to XZ. Where is this XZ? Ito yung X and Z. And we have here the cutting plane. Here is the cutting plane that is parallel to the XZ plane. And let us imagine that this vessel will be cut by this plane so that when we cut this section, we have here the exploratory section. Now let us try to imagine that we consider isolating the lower part of this exploratory section. And so when we have that, we shall have this as our isolated view of the lower part. And because of the pressure inside, we would expect that this lower part will be pushed against the upper part, and there will be a bursting effect that will be created or developed on this section of the vessel. And so there is what we call the bursting effect due to the pressure inside and this cross-sectional area. And due to this bursting effect, there will be a resisting force that would be developed along the circumference of that cut section, and this will create a stress on that section. Now suppose that we consider the same spherical tank, but this time we try to consider the exploratory section be defined by or be parallel to the XY plane. Here is our XY plane and here is our cutting plane. Now if we are to pass this plane along this vessel so that this vessel will be cut into two, then this is what will happen. Now if we are going to isolate the right part of the section, or imagine that the two parts shall be separated, then this is what will happen. We will be seeing that the right part to be isolated from the other part. And because of the pressure inside, the tendency of the pressure is to push away the right part against the left part, and that is what we call the bursting effect that will be developed on the section that is cut. And the magnitude of this P again shall be equal to the product of this internal pressure multiplied by this area of this cut section. And due to this bursting effect, there will be now a tensile load that will be developed along this section, which will resist the bursting effect and will cause stress along that section. And because the dimension of this vessel is the same in the XY plane or in the XZ plane, therefore the stress developed will be the same because the magnitude of the bursting effect will be the same. And so if we have this part, let's say for example we have the K section and we consider the cutting plane to be parallel or to be parallel to Y and Z plane. So you have the Y and Z plane. Imagine that this is our YZ plane. Kapag hinati natin siya, pinadaan doon sa ating section, then the section will be cut into two. And again, if we are to isolate the part, okay, we will be seeing here the magnitude of the pressure, the bursting effect. Sabi nga dito, due to the internal pressure, PI, or sometimes the pressure is not just the internal pressure but the pressure difference between the internal and surrounding pressure. Sometimes kasi kapag medyo mataas o merong impact ang pressure outside, then it's not actually, okay, the bursting effect is not only due to the internal pressure but the pressure difference between the surrounding and the internal pressure. It is of course expected that the internal pressure shall be greater than the surrounding pressure. And we have here P sub I. P sub I would refer to the internal pressure or the pressure difference between the internal pressure and the surrounding pressure. So that there will be a bursting effect P, F that will be developed. And this bursting effect will be equal to the magnitude of that P multiplied by the area, where the area, if we will be looking on this from this side, then we will be seeing an area which is equal to circular, whose diameter shall be the diameter of the sphere. And therefore, the bursting effect that will be developed shall be equal to the product of the pressure difference or the pressure inside multiplied by pi the square over 4. And again, due to this bursting effect, there will be now a resisting force that will be developed that will be acting on the circumference of the wall, on the side. And this will be maybe sum up to have a magnitude equal to T. And so if we're going to consider the condition of equilibrium, therefore this T shall be equal to the bursting effect, such that you have T equal to the bursting effect. And so, if we substitute the value of the bursting effect in the relationship, therefore, the magnitude of the tensile force acting on this wall shall also be equal to the pressure inside multiplied by pi the square over 4. And if this will be used to calculate for the stress in the vessel, having the ratio of the tensile load over the resisting area, again, how do we define the resisting area? It is the area or the circumference of the circle multiplied by the thickness. And the circumference of the circle is defined by what? By the pi multiplied by t, where the resisting area is the circumference multiplied by the thickness of the wall. So that when this is substituted in the formula, you have P times pi the square over 4 multiplied by pi dt. In this formula, we'll have pi will cancel as well as d, and you will be having a formula equal to pd over 4t. And you would notice that this formula is similar or the same as the formula that we have computed for the longitudinal stress of a cylindrical tank. Why is that so? Because the projected area is also in the form of a circle, just like when you have a spherical tank. Now, the second type of vessel is that when the vessel have the same dimensions in two directions, and the third dimensions is different. Ano mangyayari? Sabihin nun, the vessel will have the same stress in the same directions or in the two directions, having the same magnitude of or having the same dimensions. And there will be the third stress which shall be defined to be acting along the other direction. Anong halimbawa? Okay, halimbawa, we have here a capsulized form of a vessel, not a cylinder, but in the form of a capsule, where this will be maybe made up of a cylinder that is surmounted or covered by a hemisphere on top and at the bottom. Isa siyang cylinder at mayroon siyang nakapatong na kalahati ng parang bola sa taas at sa baba, na kung saan ang dimension, ang diameter ng hemisphere dito is the same as the diameter of the cylinder. Pag sinabi natin pareho ng dimension, if we will have here the x and the y, the dimensions, okay, are the same, while the third dimension is in this direction. Okay, now since we have, as I have said, we consider that we first take the stress that will be developed along this axis, along that axis. So because we have that along the axis, we may consider here any section along that section, itong section na pwede natin tawagin section AA, B, C, C, and D along this section, doon sa cylindrical part ng ating vessel. And when we pass an exploratory section, say for example, nag-cut tayo ng section AA, o kaya nag-cut tayo ng section BB, o kaya nag-cut tayo sa section CC, o kaya naman ay doon sa section DD, we will be getting the same magnitude of the stress. And how do we compute for the magnitude of the stress? We try to isolate one half or the other part, maybe the upper part or the lower part. In this case, I have isolated the lower part. And as I have been discussing, this lower part is being pushed against the upper part by the bursting force due to the pressure inside. Ba? Sabi nga dyan, due to the internal pressure P sub I, or the pressure difference. Okay? Again, I am referring to the pressure difference as the pressure between the internal and the surrounding. The wall of the vessel is subjected to tensile stress caused by the bursting effect of the pressure. And how do we compute for the bursting effect? Ito yung ating bursting effect na makikita, And that bursting effect or bursting force shall be equal to the area. Now, how do we compute for this bursting force? Pakita natin yung area. Ito yung area, Area will be in the form of a circle having a diameter equal to D. Now, the magnitude of this bursting force is equal to the product of this multiplied by this area. And again, this will be multiplied. Okay, so we will have, and if we are going to apply, the condition of equilibrium, therefore this T shall be equal to that of the bursting F. And that is equal to, F being equal to P multiplied by the projected area. Therefore, F is equal to P times pi d square over 4. Or, we're going to compute for that stress that will be developed on the tension of the wall. Therefore, we have tensile stress or tensile load divided by the resisting area, and that resisting area is equal to the circumference of the projected area multiplied by the thickness of the wall. And again, if that would be substituted here, ito natin yung area, yung nagbibilik na yun na kulay green and yellow. Now, that will be substituted. Our formula becomes P times pi d square over 4 divided by pi d. And again, this will be cancelled. And so you'll have here PD over 40. And you will notice that it is the same as that of the stress developed on the sphere as well as the stress developed along the longitudinal direction of the cylindrical tank. Again, bakit ko sinabing gano'n? Kasi nga, ang area that is cut by the cutting plane is in the same shape as a circle. And therefore, they will be getting the same stress. Now, suppose that we consider the same tank, but this time our cutting plane is in this direction, is the vertical, cutting it in the transverse direction, transverse section of the tank. Now, what will happen if we're going to isolate the right part? Paghiwalayin natin sila, and this is what we will get. This is what we will have. This is now the right part of the exploratory section. And this right part of the exploratory section is again subjected due to the pressure inside by bursting force F. And that bursting force F shall be equal to the pressure multiplied by the area projected. Okay, area cut by the cutting section projected along the plane perpendicular to this direction. Kung titignan natin yan, ano yung tsura niya? Okay, ito yung makikita nating direction ng ating yan. Now, if we're going to examine this area would be is composed actually of three different geometric figure and can be simplified into this form. Tingnan natin mabuti ano. Yung dalawang yan, pag hinati natin, yung dalawang mabubuo na parang circle. Kasi ito ay hemisphere, ano? So magiging circle matitira dyan. Kaya ano ngayon ating magiging area? We have area of the rectangle here and area of the circle there. So that the total bursting force shall be equal to the product of the pressure inside multiplied by the sum of area sub 1 plus area sub 2, where area sub 1 is the rectangular part of the cross section, and area sub 2 is the total area of the upper part and the lower part, which in this case is in the form of a circle. Kaya pag kinumpit natin yan, area ng rectangle plus area ng circle. And therefore, the bursting effect shall be acting all over the circumference of the area, which causes the wall to be subjected to tensile load. Ito yun. Kung titignan natin yung force na yun, nakita natin yung kulay blue na yun. And the total of which is equal to 2. And if we're going to apply the condition of equilibrium, again, this tensile load is equal to the bursting force F. And therefore, you have this. Yan, which is equal to the pressure inside multiplied by the product sum of area 1 plus area sub 2. And if we're going to solve for the tension, tension on the wall of the vessel, tension of the wall of the vessel is also the same as the tensile load over the resisting area. Ba? So, ganun yung makiyari, ano? Where the resisting area is equal to the circumference. Circumference naman ng ating projected area. Kung titignan natin dito, ano ba yung circumference? Ito yung circumference ng kulay dilaw na nakikita natin dito. Which actually, in this case, is the sum of the two lengths of the cylinder and the circumference of the circle. So you have twice this length and the circumference of the circle. Now, to let us understand further or better the concept that I have just developed, let us have here an example, ano? So that we could follow how to apply the concept in dealing with problems in thin-walled pressure vessel. And here is the problem. A tank shown in the figure is fabricated from a 3.2 millimeter thick steel plate, and we are required to determine the different stresses developed in the tank. That means the longitudinal and the circumferential stresses caused by an internal stress of 0.85 megapascal. Now here is our tank. The tank has the following dimension. Here is the tank. The thickness of that cylinder. The tank is 450 millimeter. It is composed of a rectangle that is has a length of 600 millimeter, and this is actually in the form of a semicircle. Semicircle yung part na yan. Kaya kung titignan natin yan, yung binubuo siya ng rectangle and dalawang semicircle on both ends of the rectangle. The length of the tank is not identified, not given. And we are required here to find for the stresses developed. Ito yung sinasabi natin a vessel that have different dimensions in the three directions. So, iba yung dimension niya in this direction, iba rin yung dimension in this direction, at lalong iba rin yung dimension in that direction. Kaya meron tayo ganun rin klase ng tangke. Kapag ganito yung tangke natin, asahan natin, ang stresses na makukuha natin, tatlo din. One stress is in this direction, the other one is in this direction, and the other one is in the direction along the longitudinal. So, ipapakita natin dito. Kapag ito hinati natin, dinaan natin ng cutting plane direction, makakakuha tayo ng isang stress. Ano? So we have one stress. If the vessel is cut by this cutting plane, then we also have another stress. And if the vessel is cut by this cutting plane, we have another stress. So doon sinasabi natin ditong determine the different stresses sa makatuwid. Ang hinahanap natin, tatlong different stresses. Pag sinabi ditong longitudinal, edi dito sa stress na ito, di ba? Yan stress na ito. Pag sinabi ng circumferential, dalawa yung stress sa circumferential. Yung stress dito at saka yung stress dito. They are both circumferential stress. Ano? Doon sa hinahanap natin, tatlo. Ano? Kaya ano pa natin kukunin yan? So puntahan natin yan. Halimbawa, meron tayo ditong section. Ano? Ito yung ating section. So we'll be getting the circumferential stress in this section. So let us try to isolate the part. And we try to consider isolate the right part of that exploratory section. So this right part will be subjected to bursting effect F due to the pressure inside. Ano? And that bursting effect F will be equal to the product of this pressure inside multiplied by the area projected. So pag pinroject natin yan, ito yung makikita natin actually. Ano? Itong ating shaded portion. Yan yung ating projected area. Having a dimension of 450 by the length L. Kaya yung ating bursting effect shall be equal to the pressure inside multiplied by projected area, and that when we substitute the value, it is equal to 0.85 multiplied by 450 multiplied by the length L. So if this will be simplified, okay, I have 382.5 L. The resulting unit, if this is multiplied, is still in MPa millimeter. But if this will be simplified, this will yield to an equation or to a unit of a Newton. So I still sinama ko muna dito yung mga resulting unit because later on, para hindi makakonfuse sa atin when we obtain the final resulting unit. So this will be causing now a stress on the wall. Okay? And then solving for the stress, we shall have stress equal to the tensile load over the resisting area. Okay, the bursting effect is equal to 382.5 L megapascal millimeter. So if that would be substituted here, and our resisting area is twice the length multiplied by 3.2. Maybe you would be asking why twice the length only? Why we have not considered this part of this vessel? I will explain to you later on. The reason why. So when we cancel that L and that of the millimeter, we will be having a resulting unit of megapascal, and so the stress becomes equal to 5.76653 in megapascal. So again, sinabi ko nga, maring tanong nyo, why is it that in the computation of the resisting area, only the side wall is considered? Kung mapapasin ninyo, in the formula that I have used here, I only considered here 2L. Yet, there is this particular area that is also part of this circumference. Why only this part? Ganito yung sagot, because the L is not given. So, if you say the L could be any value. Could be short and could be long. The problem is, if L is very, very long, napakahaba niya, then this shape or this one will be in the form of a part, and this part of the section will now be inefficient or ineffective in supporting the tensile stress that will be developed somewhere here. And for us to have a safe design or safe computation of the maximum stress, we may consider it to be negligible. The support or the contribution of this wall or this part of the wall may be considered negligible, and so therefore we will be expecting that's only the wall of the vessel that is supporting the stress. And that's why the only resisting area is taken to be twice of the length of the wall multiplied by the thickness of the wall. Okay, now let us consider that we imagine that the same section be cut by another plane, and this time we cut it in this direction. Ngayon, pag iniiwanan natin siya, ito yung ating makikita, and because of the pressure inside, this will be subjected to a bursting force F, and the magnitude of the bursting force F is equal to the value of this P multiplied by the projected area. And what is the projected area? The projected area will be equal to this length. Ito mismong shaded portion nakita natin, whose dimension is 10,050 multiplied by L. And so if this will be substituted, F is equal to the pressure inside multiplied by the projected area, and that is equal to 0.85. The projected area is equal to, 1050 multiplied by L, and that is equal to 892.5 L megapascal millimeter. If this will be simplified, the resulting unit of F will become Newton, because if L is in millimeter, and then Newton per millimeter square will cancel, ano? Kaya matita dito is millimeter. Now, if this will be substituted here, okay, in the formula for the stress is the ratio of the tensile load divided by the resisting area, then our stress becomes 892.5 L, okay, megapascal millimeter divided by 2, L multiplied by 3.2. And then the result will be, okay, equal to 139.4531 megapascal. With the same explanation that, okay, the thickness of the cover here is not considered in the computation, because it is assumed that this is ineffective or less effective, okay, in contributing for the resisting the stress developed on the wall. It is assumed that it's only the wall that will carry the stress. And for the third stress that will be developed is that when we pass an exploratory section in this direction, we shall be getting here the longitudinal stress that is taken in this part. So if we will be isolating the lower part, this is what we would see. Ba? Kaya pag in-isolate natin yan, okay, so yeah, due to the pressure inside, meron tayong 0.85 megapascal. This will now be causing that this lower part will be pushed against the upper part, and this is our bursting effect. And due to that, okay, ang ating bursting effect will be the product of this pressure multiplied by the area, projected area. Now, how do we get the projected area? The projected area will be defined by this area. Yun yung area na yun. Itong area nasa ibabaw nakita natin. And it's actually made up of two different shapes. One is in the form of a, okay, yan, makita natin babago, no? Yan, rectangle, having a dimension of 600 and 450, ano? 450. And the other one is this, yung bago namang kabila, and we consider this as the sum of the two, okay, semicircle. And therefore, when we combine the two, we have here actually a circular, okay, section. So that when we simplify that, okay, what happened? Okay, the product of the force is equal to 0.85 multiplied by the sum of A1 and A2. That when we substitute the value, you have 600 multiplied by 450 is actually the rectangular part, whereas pi times 450 squared over 4 is actually the sum of A1, A2, the two A2s at the ends of the rectangle. It is actually in the form of a circle. And so when we simplify that, you have F equal to 364,686.7 Newton. So that if this will be substituted for, okay, in solving for the stress, you have tensile load over the resisting area, and therefore it will be equal to, okay, 364,686.7 divided by the circumference, that is twice of the 600, and the circumference of the circle multiplied by the thickness of 3.2. And so when we simplify, we'll be getting a stress equal to 43.6025 megapascal. I hope, guys, that you're able to follow the discussion that I have presented to you and the sample problems that I have given. Sana ay patuloy niyo akong subaybayan sa ginagawang discussions with our mechanics of deformable bodies by subscribing to this channel. And if you have friends that tingin mo ay kailangan din ng ganitong klase ng discussion, you may share this lecture so that they may also be informed of these uploads. Once again, thank you very much for watching.